Okay, so moving on, let's get into the lasers. Okay, I have a visitor right here. What do you want? Of course, he wants to come here and bug me on my very last lecture I'm recording. Ethan, you want to say hi to everybody?
Hi.
Say hi to the YouTubes.
Hi.
Okay, go away. I'm just kidding. You can grab a game if you want. Okay, I'm just carrying on. So let's talk about lasers. Okay, so laser is an acronym that stands for light amplification by stimulated emission of radiation. Okay, so let's go through this acronym. Okay, so where do we get the stimulated emission from? Okay, so here are two examples, a 3-level laser and a 4-level laser. Okay, so in the 3-level laser, some source of energy that we call a pump promotes everything to some excited level. And in this case, an I is used here to stand for intermediary level. Hey, go away. I'm recording a video. Get out of here. I'll be done soon. Debating if I'm going to edit this. I don't think so. So this is some intermediate state that we pump up to. Okay. And the laser action is actually given by now a decay of energy from state A to the ground state. Okay. And so what that ends up creating, having this as a minimum of a 3-level, makes what we call a population inversion. Okay. So we know that normal thermal equilibrium suggests that 99% or more of everything is in the ground state, right? And we might have one molecule out of a million that's in an excited state. But when we do this pump, the goal of this pump is to create a population inversion. And the way that this population inversion is created is through this either 3-level or 4-level system. So the way that this works is the pump occurs very fast, okay? The laser emission is also typically very fast, but then the decay from this state I to state A is typically slow, okay? And so what that means is it creates like a stopgap, if you will. So we can pump everything up to this excited state really quickly, okay? There is a non-radiative transfer of energy from state I down to state A, and that's slow. And then, of course, as soon as the molecules get into state A, they jump back down to the ground state very fast, but then return back to the state I really fast, okay? So there's a lag time as these things go round and round, which leaves the ground state depleted, okay? And what works even better at creating a population inversion is a 4-level laser, okay, for the same argument, right? We recognize that these steps will be really fast, the steps that involve emitting light, and the non-radiative transfers will be fairly slow. And so what this ends up creating is, again, another kind of lag time for things to accumulate in this upper level, okay? So that's the stimulated emission part. Where does the light amplification part come from? Well, as we create this population inversion, when everything is falling back down to the ground state, those will all have the same frequency, right? Because we're talking about the same energy level. And the size of this laser, so this is what we call the laser cavity, it is created as a very specific size, and that size are going to be half integers of the wavelength from the laser action. And so what that means is because only integer waves can fit in this box, they constructively interfere to amplify the amount of light emitted, right? So all of these right here will say constructive interference, okay? And that's based entirely on this cavity size. If we just create some laser cavity with arbitrary dimension, we're not going to necessarily get laser action out of it. So each laser has to be uniquely designed based on the wavelength of the laser action and making, some cavity, right? We call it the cavity, but it's really a box that contains the molecules that we want to create a laser from, okay? So that's how we get the amplification of light.